Okay, welcome back. This is lecture 23, I think, and today's date is February 17th. So we are going to start the next unit, and this unit is going to deal with more advanced topologies of the common source amplifier itself. Okay. Advanced topologies okay, let me not say common source amplifier, I will say this is advanced topologies for biasing circuits. Okay. So I want all of you to, we are starting a new topic, so pay attention. So even if you have not followed something earlier, you can catch up. Okay. All right. So what is it that we have in mind? What was the standard biasing circuit that we have used so far? Right. The standard biasing circuit we have discussed so far is the one where you have two resistors. That's going to VDD, and I have this. That is your biasing arrangement, RA, RB, and that was your RD. Correct? All right. Now, based on this, what did you do? Graphically, what did this entire thing achieve? It basically put you on some point on this curve, which was ID versus ID versus VDS for some value of VGS. So using all of this, you made this VGS. So you know this was some VGS1. So basically, you set your operating point somewhere there. Correct? That was your Q point, and this corresponded to some value of ID and VGS. Yeah, but once you are in saturation, it is independent of VD, right? This is what does that line mean? That line is basically the value of VGS is VGS1, so I will drop it there. So this is some ID1 and VGS1. Okay. What is the gain for this system? What's your GM? Okay, so can you tell me what GM is? Tell me the final expressions. Good. 2ID by? That is one expression. Then of 2 times there was mu1 Cox W by L times ID. Then what is the expression? The 3 expressions, right? What are the there was a root. Was it K or 2K? It was just K, right? So it was the mu Cox W by L into VGS minus T. Okay. So what does this tell you? This tells you that this transconductance GM and hence your gain is a function of the bias values. Correct? You have to if you want a certain gain, you have to choose the bias point such that you get that gain. Okay. I want you to think about the following. Say for some reason, and I can tell you the reason also, you have experienced this reason also, a manufacturer makes like thousands of transistors. If you take 2 transistors, nominally they are the same number, both are BC177, right? But will they have the same value of the various parameters? Can never be like that, right? T will be nominally say 0.5 volts, but the manufacturer value things fall in some range around 0.5. just like resistors, right? You had 1k, if it is 1k, it may mean 1 point something to 0.99 to 1 point something, correct? So there's a tolerance in everything. So the aim of these advanced topologies is to see if you can eliminate the sensitivity or reduce the sensitivity of the output performance of your amplifier to all of these variations. Okay, that's the goal. Now keeping that in mind, look at this GM, okay, and as I mentioned here, you can set this GM in two ways. One is, I can, for example, fix my VG, or I can fix my current, correct? So I can say that method 1 is to say I fix my VGS. Method 2 is fix my ID. They are not. How is it a function? It is, correct. So this is a good point. What that function T in saturation was mu and Cox W into VGS minus VT squared whole thing divided by. So yes, ID is a function of VGS. However, you notice that it is also a function of mu and Cox VT. These things are not going to be the same for all devices. So so one device will have VT as 0.5, another one will have 0.5. It's only 10% off, right? So if you want to set your operating point, or rather if you want to set your, what these expressions tell you is that about the first expression. Look at the second and the third expressions. This, what are these methods for? These are to obtain some GM. Correct? I want some GM, I can do two things. I can fix my VGS. If I fix my VGS, I can use this formula. Correct? I can use this formula and obtain my GM. Correct? If I were to fix my ID, which one should I use? I can use the second formula to obtain my GM. I can work with both varying, but that's not really helpful for me. Okay. Now, can you tell me the density of GM in these two approaches to these various other parameters? So let me just call this mu and Cox, like I had earlier. Let me say mu and Cox L. Okay, actually mu and Cox is usually okay, but for this particular purpose I don't care about that. I'm going to just put Cox W by L as K. Okay, not the old K, it's another K. Okay. So now can you tell me the sensitivity of these things? So I'll call this as expression 1, this is expression 2, and this is expression 3. Okay. So okay, so actually not call this, just to make everything cleaner, I'll call that A, method B. Method A uses formula 3. Method B uses formula 2. Okay. Now I want you to tell me what is delta GM by G for this method 3. What is it going to be? It will become, if I write 1, you can tell me the others. So this, look at form 3, it will be basically be delta K by K plus delta VT by T plus, is that right? No, it is wrong. It's wrong. So, okay, at least you got a hint as to what it should be. So, can you tell me how it is? It will be delta K into, what will it be? That it's all, is it that? Is it just that? Plus, right? Yeah, so it is correct. What I was writing was correct. Plus delta T by VT. Is this right? You take a logarithm. How did you do this? Take log, so you will get this term, and then d log by that will give you, right? Just for people who So if I have something, if I have some function y equal to some alpha time alpha in some x plus beta, which is what we have, right? I want to find out the sensitivity of y to parameters x and so to parameters I and beta. So how would you do this? So I will say log is equal to log alpha plus log of x plus beta. So what does this mean? This means d. So then I take a derivative of everything. What will I have? So I will have d of log y. What would this be? This is this will be dy by y, right? D of log alpha would be d alpha by and similarly your d of log x plus beta would be d of x plus beta by x plus beta, which is nothing but d beta by x plus beta. Okay, so we made a mistake in the previous thing. So if your expression was right, so this is what we need. So that's why something was not okay. So if you go back here, you will have dk by k and delta vt and you will have into 1 by which one? Okay, sorry. Yeah. No, minus won't come. No. Yeah, but usually errors, to take errors, you have to add errors, right? So, because you can have a negative there. Yeah. So, when you are doing errors, you take the positive. Okay. And then, because your VGS is constant in this. In this other mode, so in this mode, what I get? I'll get Gm by Gm as equal to half delta k by k plus what? That's all, right? Because your ID is fixed. Okay. So out of these two, which do you think will, for the same variation, same manufacturer spread in Vt and K, which of these is a better way? Second one is a better way, right? So one gives you so that is a better way to fix my operating point Q. Does every this? Right? Because in this term you have a delta k by k. Here that has become delta k by k by 2. Plus there is other variation. So this is definitely going to be less than that. Correct? Yes. So what I am saying is, if you can come up with a topology wherein you use the current to fix the operating point instead of the voltage to fix the operating point, it is better. What do you mean by better? So what I should say is, instead of better, qualify that saying that this is a more simple way to fix Q, right? So that it is a little less variant on the exact device that you use. Okay. All right. So this was basically error analysis 101, right? And this is correct. So your errors, right? When you take errors, take so your delta y by y would be essentially delta alpha by alpha plus delta beta by x plus beta. Okay. Now let's proceed. So we just figured that we want to have a currents to set the bias point. So biasing current source or using. Okay, let's talk about this again carefully. I had a situation earlier where I had a MOSFET. Now I am going to eat up all the resistors and all that. I don't want all that. So if I have some voltage here, what voltage was this? This is my VDS. And say I apply a no small signal bias voltage. I apply VGS. Okay. When all happens, some current flows here. So if I call this VG1, say I1 flows here. Okay. This is what we have learnt already. How about this situation? So I ask the question, take this and say I put a current source this way. And this one exactly I1. So the experiment I am doing is put voltage sources VGS1 and VDS1 so that device is in saturation. Okay. I am going to measure the current. So I measure I1. Okay. Here I am going to set my current using a current source with value 1. The question I am asking is, what is VS1? What is VGS? Think about that. Now I put a voltmeter here. Okay. This is a voltmeter. So what does this voltmeter read? Okay. Why am I asking question? Because in the previous discussion what we saw was that if I want to get a GM and I know that the parameters of my MOSFET are going to be, then I can do one of two things. One is I can set my gate source voltage such that I get a certain value of GM. That is use this expression, right? That is using expression 3. If I know my VGS, my VT, if I set VGS, I will get what? Some GM. Another way is I can pass some amount of current through the transistor. In that case also I will get a certain value of GM. Okay. And analysis tells that the second method that method B, where I am fixing the current, is actually less sensitive to variations in the various parameters. In fact, it is invariant to what? This is invariant to VT variation, right? This is invariant VT variation. One is dependent on both. Okay. So now can you do something? So this system basically uses the VGS, right? This method uses, this is what we have done so far. This uses voltage to set the bias point. What about this? Does this work? We discussed this in the tutorial also. We discussed it. Okay. So can you tell me what this voltmeter will read? No. This device not, the MOSFET is not binaural. Very, very important. How does the MOSFET work? I have a MOSFET, right? There is a gate and there is this thing. When I apply a gate voltage here, electron here, right? Then when you apply some kind of voltage across this, right? If is the drain and this is the source, if this is VDS minus, then some current will flow. That's how the MOSFET. you cannot pass a current through the channel and expect an inversion layer to form. The inversion will form only if you have a voltage. So this method, though looks attractive, the important take home over here is this will not set any bias point. Okay. In fact, I don't think you can tell what the voltage value will be. Why should it be 0? It can be any. Definitely, I don't think you can tell what it will be. Voltage of current source, that's okay. That is allowed. Right? So, source will cry because it's just a floating point, right? Floating point. It's not because of the current. If there is no inversion channel here, no current is flowing, that gate voltage is it's connected to the metal corresponding to the capacitor. The other side, there's nothing. So basically it's an indeterminate voltage. Correct? So this will not allow you to do the biasing with current. So we have to look at something more intelligent. Okay. So let's proceed. Now let us consider the following situation. So what is the solution to this? The solution can be the following. I have a MOSFET. I have source here.
But I put a voltage source at the top.
There is some voltage. Obviously, there has some voltage, right? Otherwise, no current will flow. There is some voltage there. That's why it is flowing. Well, no need. Okay. Sorry. Forget that. Okay. There is some current source there. This is not sufficient transistor to work. What you need instead is, in addition to all of this, you need to have a gate source voltage here. You need to have a gate source voltage. Right? You need to have a gate source voltage. But what you can do is that you can do something else such that the value of this gate source voltage is consistent with ID flow through the device. So the solution is to use a current source and a voltage source, right? There are many ways of doing it, so let us not jump too fast. I am trying to develop this systematic way. And however, your VGS must be automagic, cooking up a word, but makes sense, right? Should be automatic, should be magic. So automagically chosen to consist with ID1. It means that you had a function for ID, right? I equal to K. Exactly. So what I am saying is, if I set my ID here, the value of VGS must be that, right? So yes, one way is somebody there, intelligent fellow, looks at what is the ID flowing. Say ID is 100 microamps. I know my VT. Quickly calculate what should be my VGS, and I'll put it there. Okay, but as I just described, that is not a very practical way of doing it. It has to be automagic. So we have to think of a way where it automatically finds what is the value of VGS that is required in order to have a consistent value of current flowing through the transistor. Okay, so that is the solution. Is everyone with me so far? Don't lose me. If you lose me now, you will lose me for the next 3 weeks. So lose me here. If you are stuck, ask questions, we can clarify again. Right? So far what have we done? What are we trying to do? Ishita. No. What's the whole aim of everything? Yes, we're trying to make our circuits less sensitive to variations in parameters. Manufacturing variations in parameters. Many of these parameters vary with temperature. Stability varies with temperature. VT varies with temperature. Right? So you don't want these variations to trouble you. Right? Otherwise you make amplifier works well here, you get to the mountain, it stops working. You don't want that. So that is the goal. So we found out first that it's better if we set the bias point using a current rather than a voltage. Now we are trying to see how we can set the bias point using a current. We ruled out just using a current source. If you use just a current source, the device will turn on at all. Right? Because the device is not a bilateral device. Bilateral device means that like a resistor. In a resistor, if I take a resistor, okay, what is bilateral? I take for example, we did this, right? Let me take some network. Right? And all of this is my port network. And say I energize this with some voltage plus minus. If I energize this V1, or let me energize this with VA, okay, and say a current of I okay, let's say that a current of IB flows here. Okay. Now if you take the same system, if I take the same system and if I replace this with a current source whose value is ideally IB, and I measure the voltage here, this voltage be VA. What are these things called? What did we discuss this in the context of reciprocity? Right? So for reciprocity you needed the system to be bilateral. On the other hand, just to put it in context, if I were to take this situation, okay, if instead of this box, so this is a unilateral system, okay, I am going to discuss this. If I had, for example, let me say, so I have some voltage in, say I have a dependent source here, some k times V alpha, I will call this as V alpha, okay. It's a very simple system, right? Right? Now, in this system, if I were to energize with A, what would be my voltage here? Right? This voltage would be A times V A. However, if I take this system, right? If I take system and as he pointed out, if I pay VA here and ask the question, what is here? What is that? It's not going to work, right? So this is unilateral. It takes what is on the left and it calculates something on the right. If you take something on the right, it's not going to give you something on the left. Right? So your MOSFET also is like that. Given a input VS, there isn't flowing. If you pass a current, you are not going to get that same voltage on the input. Right? It's a unilateral device. So that's the point. Is that clear? Which one? Second case? What about that? No. it does not mean anything like that. It means only what I have written. Right? We are connecting a voltage source to the output whose value kVA. I am asking you what is the value of the voltage on the input. You can't tell me what it is. Because there is no connection that goes from right to left. The dependent source is dependent on what is the voltage on the left. It is not a thing where you move this up and that also moves up. It's not that. Right? There's no connection. So that's what I was trying to tell you. Okay, is that clear now? Okay. I think this is it. Okay. So the solution is that I can have a current my output. I can use a source on the output to set the bias point. However, I will also need to choose my VGS in an intelligent way. Right? So this VGS now has to be a smart VGS, like a smart city. Right? So why should it be smart? Because say I have chosen some value of ID, okay, and some current is flowing, right? Now say temperature increases, so my VT has changed, which means what should happen to VGS? It should also change. Otherwise, that will no longer be consistent with ID. Assume ID has not changed, the current source, right? Assume the ID is always pumping 100 microamps, and I am increasing the temperature, right? So this VGS now has to smartly changes in VT, right? So it's an intelligent problem, right? It's an interesting problem. So clearly it is at one level higher than what we have done so far. So far we never had to think about this kind of smart stuff. Okay, so now we'll move towards the solution and let's see if we can approach something today. Everyone with me? If you are not, please me. Okay. Now consider the following situation. What am I trying to do now? I am trying to make this VGS intelligent. Okay. That's what I am trying to do. Now let me consider the following situation where say I have that current source, okay, and I have this here, and there is some VGS I have chosen. Okay, now this is what we are trying to work with, right? Trying to make this VGS a smart VGS. Okay, so before you go there, let me just think of this simpler system. I say I have a current. Let this current source have some value I1. Okay. Let me connect another current source here with value I2. Is this a valid connection? No. Why? Can be same. Okay. But I can fudge a little bit because I have discussed there are all these capacitors in the circuit. Correct? So this circuit will never be just two current sources. Right? So there are some can you guess why I have drawn it side by side? This I2 is essentially like this MOSFET. That's the connection that I want to make. That's why I have drawn it side by side. Okay. So if it is not the value that you want. Okay. So there are some capacitors. I'm going to just say that there is some small capacitor sitting. Okay. This is a valid connection, right? Now you can have two current sources with a capacitor. That's a valid connection even if I1 not equal to I2. Right? If the capacitor were not there, you can't have two current sources fighting with each other. That's not allowed. Okay. All right. Now, can you tell me what is the value of this voltage? Let me call this voltage, this node X. Can you tell me what Vx? Is it possible to tell me what Vx is? No. Why? But there is a capacitor also. Right? There is a capacitor there. Yes. So, if my I1 were greater than I2, what happened to Vx? So the that is flowing here is I1 minus I2. Correct? It's a current source. If you have a capacitor with a current source, how is the voltage going to be? If I take assume some current source and capacitor, so I call this I and C, and what is this voltage V going to be? Integral 1 by C I dt, right? Because this is but voltage equal to charge by capacitance, right? We have done this. In fact, I think I gave you a quiz question also on this. My first ever question, right? Madhav is laughing. Fond memories. Right? So, what happens now to this? What happens now if I1 is greater than I2? What will happen to Vx? It will increase with time, right? It will increase. What happens if I1 is less than I2? It will decrease. Yeah, otherwise it will go negative, right? Why not? This is just two different current sources. I can connect them like that. No harm. The two ideal current sources, I am just connecting them. Why should one be more than the other? Right? There is no real requirement like that. So, what about situation when I1 equal to I2? This Vx will constant. Correct? Everyone with me now? Okay. Now we make the connection that I had this, right? The reason I drew this was so that I can do this. Now, I am connection that this whole thing in the bottom right is essentially, this bottom thing is essentially a current source, right? Similar. Okay. So now let us just do it the following way, that capacitor. Yeah, it's okay. Okay, you have capacitor, nothing harm. Now, let me just redraw this circuit again, because you can make the connection that this is nothing but that, right? Say now that I want a current of I ref to flow here. Okay, I want some reference current to flow through this device. So, maybe let me just go to the next page. Okay, so I have this situation now where I have a source and the value of the current source I know is some reference value. Okay, then I have a MOSFET here and I have some thing here. It means we want to make this thing smart. Okay, now for some reason you have set everything up and IREF is flowing through the current source and also some IREF is flowing through the transistor. Assume that is the situation. Okay, in case depending on this value of IREF, the smart fellow, right, this fellow has set the value of yes. Okay, so the smart fellow has taken this IREF and set the value of VGS. Now say my temperature changes. Okay, and say that this IREF change so let me not say this is IREF. Let me say this is ID. So IREF is there, ID is here. the smart fellow has set, you have set VGS, set such that what? That's that your I equal to Iref, right? Say we have this, somehow you have set it. Okay. Now VT is changing. Okay. What should you do? So have to correct the VGS. Right? So basically what do you have to do? Somehow you started in a where everything is okay, right? Now from that starting point, your current has changed. The current through the transistor, say, has changed. Why is it changed? Because VT has changed, for example. Okay? Because of temperature, something like that. Mobility changed because of temperature, right? So the current that is passing through the transistor, say, has gone down. Then what you should do to VGS? You should boost your VGS up. If you boost VGS up, then the ID will increase. Okay? Now let us go back to what we had in the previous case. And then you guys can work out what one should do. Okay. So what was Vx? Vx was essentially this node, right? That was your. Now, what is your I1? So your I1 is nothing but IF. And your I2 is? Is that right? Okay. So what happens to Vx? Okay, let's this is what. So if Iref becomes an ID, we have already understood that this Vx will increase with time. And Iref is less than ID, we have understood that Vx will decrease with time. This is what will happen to this Vx. Now let us think about what we need. So I have written here that you should correct for VGS, right? So what does this correction for VGS mean?
I have to increase VGS. So I have to put another voltage source, which I can take it and put it there.
So if I were to look at this point, okay, what is the correction? What does this correction mean? Okay, the correction essentially means that if ID becomes less than Iref, what should you do to VGS? You should increase VGS, right? If you increase VGS, then ID will increase. Similarly, if ID greater than Iref, what should you do? You should decrease VGS, right? If your I flowing in the bottom was more than what you want, the current, more than the value that you want, then if you decrease your VGS, the current through the transistor will increase. So that's the smart guy. Correct? So now, looking at what I have written on top and looking at the bottom, can you tell me something?
You can use Vx to correct VGS.
Exactly. Right? Why is that?
Because the change is proportional to that.
Right? So use exactly. So look at this, right? Increase. So Vx increase if Iref is greater than ID, and if Iref greater than ID, you want to sorry. If this is this, right? ID is less than Iref, you want to increase VGS. That means your Vx is moving in the direction that you want. That means Vx is moving in the direction that you want. So you can actually think of a system like this. You can think of a system which is the trans like this, right? I have my F here. I take this voltage, correct? I can take this voltage and do what with it? I can take this voltage, do something with it. I'm not going to say what, and then I can connect it back here. right? Connection. No, let's see there. Okay, this talk here. Okay, so this is your smart right. All if you think of this, does it make sense? It's an involved concept, so I don't mind you take a couple of minutes to understand this. However, what should this, so say this is a gain block, okay, what would be the sense of it? Can it have positive sign or negative sign? Positive. Why should it have positive? Because, right, because Vx, this is your Vx. Your Vx already is the correct sense. If your current through the transistor, if ID is less than Iref, then you want to increase the VGS, and this Vx is also increasing. So you can take that Vx, multiply it if you need to, put it in here. Correct? So what will be the value of VGS now here? A smart VGS, right? So VGS is here. So the value of VGS that develops across the gain source will now be smart. If your VT changes, no problem. Your Vx will change in such a way this VGS will compensate. Right? So what kind this I use the compensation and things like that. So we discussed this in our course. This is feedback. Right? So you've got a smart source using feedback. Now that is something to look at. Okay? So the question for you is whether it is positive or negative. Okay? That I'm not, we'll discuss that next class, but let me finish what I wanted to do now. Okay? Everybody with me so far? Now, can I do this? Remove this VGS and just short it. Can I do that? It still work, right? That's also a valid solution. So we will start with this simple solution, and then we will look at other feedback systems where some advantage might come if you have a gain block there. The solution that I have drawn here is also a valid solution, right? This is
for some feeding current through the gate. So when RF and RD shifts, at instant in time, I'm feeding current.
No, you have those capacitors again. Problem, right? You keep in that there are those floating capacitors sitting there, right? There's always something there. You don't need to worry. Though we are not explicitly drawing the capacitors are floating, so they will take care of those things. The parasitic capacitors are there, right? So those capacitors will take care of things. Okay, now there is one other important that that is worth mentioning here, and the point is the following: that this point is particularly valid in integrated circuit. So this is with respect to integrated circuits. Yes. So in an integrated circuit, you multiple transistors made on the same wafer, and the temperature at one place will be roughly the same temperature on the other place. And because all transistors were made in the same step, so how is the transistor made? Just take the substrate, then they deposit the oxide, then they make the source and drain, then they deposit the metal. But they do it for all the transistors at the same time, which means that yes, I want a nominal VT of 0.5. If one transistor has a VT of 0.45, then all transistors on that wafer will VT of 0.45. So it means that in an integrated circuit, all transistors are equally bad. No one transistor may be what you want. But you know that if one transistor is a donkey, the other one is also a donkey. It's the same donkey. So you can use that. Okay. In integrated circuits, all transistors identical. Okay. There is a small caveat, which is that your tube-to-L ratio may be different for different transistors, in which case there must be a scale factor that you have to account for. But for all practical purposes, they are identical. Okay. There is one other thing we need to know. We modeled this thing at the bottom, right? We modeled this transistor at the bottom as a current source. When is that a good model? When you are in saturation. So now can you tell me whether this transistor is in saturation or not? Let me call this transistor M1. Is this transistor in saturation? Yes. Why? Because this connection is nothing but V is equal to Vg, which means VDS is equal to VGS. For saturation, what you want? Your VDS must be greater than VGS minus V. And obviously, one satisfy our requirement. Okay. No, you want to work in saturation, right? If it's not in saturation, your expression for GM and all of that, everything is different. For amplifiers, you want your transistors to be in saturation. So that's a requirement. Okay. All right. I am asking you a question here. The question I am asking is the feedback negative or positive? Okay. Think about that question. But let me just proceed with this. How do you, for sense of feedback, break the loop, change the voltage little bit, go through that path, see what the correction is going to be. You can tell me tomorrow. You tell me what is the nature of feedback. Okay. Now this is one transistor, right? Now let me remove this capacitors, but I am not worried about that. Okay. This is one transistor. This is not going to act like your amplifier. So you can assume that, now assume that I am working in we are in an integrated, because for example your op amp is an integrated circuit, right? So in an op amp all the transistors will like each other. Okay. So I have another transistor here, and transistor say has your load resistance or this drain resistance and all of that, right? And if I have to connect the load, how will that load get connected to this? Right, that load will be connected like that, right? Now, this is the transistor which is doing your amplification, some VDD. So this transistor is doing your amplification, M2. What is this M1 basically? All of what we are doing here with M1 is basically a smart VGS. M1, the way we have connected M1 ends that the value of VGS is consistent that current source IREF. Correct? So now we started with this thing. We wanted to have some value of VGS for M2, right? And wanted that VGS to be independent of various fluctuations of temperature and pros and all of that. So can I use my blue circuit to do something in the red circuit? Yes. So what can I do? I can take this guy and connect it there. Okay. So essentially what is all of this thing doing? This left hand side, right? This everything on the left hand side, right? That thing is essentially, what is it? It is as Nikhil correctly pointed out. It's just a smart okay. Now, why does this work? It works because your M1 is identical to M2. Can you tell me what is the current flowing through M2 now? Right? So the current that is flowing through will also be I, because you have set an IREF in the blue circuit. This VGS that will develop in this circuit because of this feedback will be such that M1 will constantly require IREF flow to it, and you have taken that VGS and to the red circuit, and the red circuit M2 is identical to the blue circuit M1. So the same VGS, same current flow, right? What about the GM of two things? It will be same GM, right? Because so this GM, let me cut GM1, GM2. So your GM1 will be to GM2. So okay, tell me a name for this. Anuja, can you tell me a name for this? Yes. So it's basically something that you have feed. So people take little bit of they take some license naming it. They call this a current mirror. Why is it mirror? Because it takes the IREF in that ref circuit and mirrors it in all the other circuits. Correct? Now this thing we can just draw a slightly better way and stop. Thing, right? So just to have that, I'll keep it here so all of you know what that is. Let's see if I can get. Okay, that is that. But I don't want to draw it with all these things moving from here to there, left to right, and all that. Right? I want to look a little cleaner. Right? So you can take this guy, and so this is identical to. Right? I can take this, there's a current source, correct? Then instead of the transistor facing this, I just flip the guy. Right? And then what should I connect? This X to this thing connection is, and then this other I'm going to have here, this is VDD. Okay, so we have not yet told you what value is. Leave this as VDD. There is this is your R, and I can have another identical transistor, correct, and connect that there. Say I have one more transistor, and I do, and I want the same current to flow in another transistor. So I can basically I can do this, you can't do that, right? And people like little bit of license, be careful with connection. They draw it, so they put a dot there, so it connects, this red line connects to the gate, and then they draw it through that, another dot, then they draw it through and a dot. Yeah. Okay. So this becomes your arrangement in the current. So what have we achieved with all of this? Right? So you have got a GM which is independent of what? Independent of? No. GM is independent of what? VT. GM is not independent of current. Then there's no point doing anything. Your GM is, what's your GM? GM depends on current. That's how we state. GM is dependent on current, correct? So this is our first look at one kind of more advanced topology. We have to still read this because this is the biasing circuit, right? Now we have to look at how to connect the source, how to connect the load, and then calculate the gain and do all of those things. Okay, we can do that, but I think the general idea now be clear, right? You use one transistor and you connect its drain to its gate. Okay, so this kind of connection sometimes is referred to in books. Kind of connection is referred to as a diode connect MOSFET. Okay, terminology doesn't make sense for MOSFET, but if this were a BJT, then you basically have a BJT which is that, correct? And if I connect this as, right, what does the BJT look like in this thing? Which is your P? This is N, P, N, correct? So here the semiconductor version of this will be, you have a N region, P region. Now what does this connection mean? This connection, that diode connection, right, is basically is connecting to this. So then what does whole thing look like? Right? Right. So then all of this essentially looks like a diode, right? So this is diode connected MOS idea. Okay, as an aside. The terminology, because a lot of these circuits you can find exact equivalents in the BJT world also. So because there it's like a diode, they call it diode connected MOSFET. Okay.